Okay. Okay, so I'm Matthias Vigero from ESRF. I'm a colleague of Stuart, so in the same beamline control unit. So today is a special day for me, of course, because I'm giving this talk to you guys, but also because 18 years ago, I remember it was my first talk ever at November 2004 here at PSI in the same auditorium, I guess. Or I thought it was bigger, but maybe it's the same, no?
2004, yeah. It was the same.
Well, so after some years, things get impression of getting smaller. In any ways, so I'm responsible of the BLISS project at ESRF. So I'm gonna talk about BLISS. So BLISS stands for Beamline Instrumentation Support Software, and this is the new ESRF beamline control system. So you may have heard about BLISS a lot or not, but in fact, I would like to start with a bit of a recap of the milestones for the project. So in fact, this project started in December 2015, and the first talk about BLISS was at ECALEPS in Barcelona in 2017. And we wanted to replace and to renew completely the data acquisition system we had at ESRF at that time, which was a spec for 26 years, in fact. And it was a very exciting time for us to start this project, and we were waiting for it. It's a long time, so we are very happy. And in May 2018, we had our first test with friendly users, and it was just to assess a bit the system, how it was, if the choices we made were promising for the next steps. And the goal was to be ready at the end of the ESRF upgrade. So the upgrade of ESRF started in December 2018, and we had a shutdown for 18 months. So basically the same thing as what will happen here at SLS. And to get 100 times more powerful X-ray. And so the idea was to have a new set of, renewed beamline, upgraded beamlines, and to start after the EBS shutdown with BLISS on those beamlines in order to take advantage of the new beam with the new control system. So here is a picture of the BLISS team in September 2019. So we were, I think, 7 members at that moment. But in fact, there are many more people working in the BCU for BLISS, and also other units. I would like to think about. I'm thinking about several people, but I'm not giving names. Okay, so we will see. In any way. So we started the deployment of BLISS on EBS beamlines in 2019, 2020. And like everybody in the world, we got quite perturbated by the COVID lockdown in March. So it was a bit difficult times, because it was exactly at the moment where we were trying to, normally we would have more time to work with the scientists on the beamline to do the commissioning of the system. And due to the circumstances, it was more difficult. But in any ways, in August 2020, we had a restart of user operation and with BLISS. And BLISS went to 0 in December the same year. And so now we are continuing BLISS deployment on all beamlines. And the latest version is 1.10, which was in August. So this is just to think about the project and the time it takes to completely renew control system at the synchrotron. So today, here are the BLISS beamlines at ESRF. So it's more than half of the beamlines. And well, for those who know ESRF, maybe you know some of the beamlines, but okay, the full deployment is aimed at the horizon of 2024. So today, what are the changes for experiment control systems? So I'm not even talking about controlling hardware, because it can be challenging sometimes, or I don't know, having nice trajectories with the motor controllers or whatever. I will also barely talk about what happens with new detectors that are faster and faster, like always. But there are many challenges, because as you can see, and this is the previous talk by Stuart. Now the control systems, they need to interface with graphical interfaces that can be web-based or not web-based, and also data portal. For example, ICAT at ESRF, we have a data portal for users to be able to access their data from remote, and we have the electronic logbooks. So all those systems need to operate together. People, of course, want to see live data, and today we can't have the same, let's say, because the technology evolves and everything is getting more nicer, and we need to really make a special work for user experience. So people expect to have a good look and feel and usability, and of course to run their experiment scripts and user sequences like always. So basically, the goal of a control system today is to make everything working together, and this is quite challenging. So this is where BLISS is at the heart of all this, and I will try to demonstrate, I mean, not demonstrate, but to give an overview of BLISS features and architecture so you can have a good understanding of the project. So BLISS technical choices and design principles. So it's written in Python, 100% Python. And we decided to go for what we call all-in-one solution. So to mimic a Python motto, it's high batteries included. So we provide configuration management, so to be able to take care of the beamline devices in the system, and also configuration of user sequences, everything. In fact, we have logging, so you can follow events on the system. We provide communication protocols, GPIB, Modbus, TCP. We provide primitives for that. We provide hardware drivers, because as we took from spec philosophy, we took the idea that the system should also be able to know the hardware, in fact, and connect to it directly. We provide a command line interface, the scanning engine, of course, live data display, and publishing data and saving data. So this, in fact, is made of mini frameworks. So we have like a mini framework for motion control, mini framework for regulation, for monochromator control, spectrometers, multi-channel analyzers. And like this, we are able to integrate easily new hardware. All the input-output in BLISS is based on G. So for those who know Python, this is a very technical information, but okay, it's a cooperative multitasking library. So this allows to do like threads basically, but without the burden of sometimes of threads with the preemptive behavior. And recently we added the possibility, we have the possibility to interoperate with async IO, so it's good for the future. So as I said before, we have built-in direct hardware control of a lot of devices we found at ESRF, and that probably can be found elsewhere, of course. And and we provide Tango servers extensions if, for example, we want interoperability with other systems. So, for example, at the moment we are still having spec beamlines at ESRF, but spec beamlines still want to use, I don't know, the latest Lakeshore for temperature control or whatever. So then in this case, this is integrated in BLISS. We give the Tango server, and spec can use the Lakeshore. And also, if we share hardware and some hardware only access one connection, for example, in this case, we put the Tango server in front of it, and then we talk to the Tango server. And so what is important to understand that the control code is in BLISS, and we use Tango to make it open. So we run scans with our concept of acquisition chain. So the acquisition chain for us is an essential bit of BLISS. In fact, it's a tree structure that represents the relationships between the triggering relationships between devices in the scan. So for example, if a camera is triggering, I don't know, MCA, or the motor at some position triggers the camera, then we represent that in a tree. And this is how we can define scans in BLISS, either step by step or continuous. I mean, without any difference, in fact. And so, last but not the least, data publishing is a design principle in BLISS. So we use Redis, and we ensure that acquisition is independent of the storage. So we publish data, and we have a process that can record HDF file. And as the data is published, some other processes can also listen to it and do something useful with it. And as it's decoupled, the moment of saving is not slowing down acquisition further. So to have an overview of the architecture of BLISS, this is basically the same schema I always show, but it's still valid. So we have at the very bottom, we have the beacon server, which runs Redis and provides some services for all BLISS, in fact. Then we have a communication layer. So we give the primitives for the upper layers when we want to communicate with TCP or sockets or whatever. We have hardware controllers. And on top of those hardware controllers, mini frameworks, as I said, to ease integration of same kind of hardware. So for example, you have your, I don't know, motor controller. You implement communication with the motor controller by reading the manual. Then you enter this into the framework of motion framework, and then it gets available for all the upper layers. So the upper layer, for example, is this adaptation layer for the scan. And I will not enter into very technical details here, but this is to give an overview of the system. So how is the data flow in BLISS? We have our configurations files in YAML format, so it's human readable, and we share that in many projects at ESRF today, like for example in Daiichi, it's also with a YAML configuration file. So the configuration files are ingested by the beacon server, and then from the shell we can instantiate the different objects of the beamline. And we have, for example, persistent settings. For example, if you set velocity on a motor, we keep that. So then if you restart the same session, velocity of that you set previously is the one that is applied for the motor. Of course, you can change it or go back to the config one. And we have the scanning engine. So it receives the data from the devices, and it's emitting all that to Redis. And from Redis, we have listeners for online data display, for writing the HDF file, or for online data analysis. So for online data analysis, in fact, there will be this talk from Wout this afternoon about evokes, and so this data API allows all those programs to listen to BLISS data, and there will be a poster by Luca or one of my colleagues tomorrow. And of course, from the BLISS shell, we also take care of data policy, ICAP, electronic logbook, as I explained before. It's a constellation of in fact, it's a software we have to run together. So I will make hopefully a short tour of the features which are most praised by ESRF scientists. I made a small survey before coming. So as you can see, there are 5 points. So one is Python, so we'll explain afterwards. Then it's Flint, our interactive data display tool. Then the possibility to define software axes and counters, the possibility to have software regulation loops, which is what scientists really like, and accessing BLISS data on the fly. So all the examples after that are in fact made by scientists on their beamlines themselves. So for example, on BM23, our colleague Kirill, he made this beamline health check for local context using Telegram. So he receives on his phone if everything is successful in the beamline, or if the macro has been successful. And this is good because scientists can really take advantage of the huge pattern ecosystem that exists in their own scripts, in fact. So another example is from ID11. So it's this tomography nanofocus station. So there is this axis moving at 25 degrees per second, and the detector here, the Edgar, which makes 500 frames per second. So we record 700 gigabytes per hour of contrast data. And in fact, people can write their own acquisition sequence, like the night shift macro, let's say. So in BLISS, they can directly import beamline objects. So this is done, like, for example, on this first line. Then, as I said, the whole Python ecosystem can be available. They use just normal Python functions with named arguments, default values as a normal Python. Some extra features like context managers in Python. So, for example, we give the fast shutter, we give shutter objects with context managers, but then people can use them in their script. And they call continuous hardware synchronized scans. So those scans, in fact, are generic, but adapted, of course, for each beamline, because each beamline has different hardware. So this is part of BLISS as well. Then we have Flint, the interactive display tool. So it's a companion application that is based on ESRF-EBS, which is a Qt toolkit. So it's not yet a web application, but in the future it will be. And today it provides live display of BLISS scans, custom plotting, interactive control. So what I'm talking about is, for example, you can say, okay, I want to edit region of interest in my, to receive a sum of a part of the image, for example, the pixels on this camera. So I can pull this command, and then it displays Flint, and then you can define different kind of region of interest, arcrows or square, or well, there are different options. And when user apply, it goes back to the sequence, and so you can write sequence, interactive sequence with Flint. User can click on Flint. So another thing that scientists really like is the Photoaxis. So this is an example from BM32, allowed diffraction. So they made experimentally, they collected data to have energy to brag abacus, let's say. And then they can easily write a calculation controller. So then there is only a few methods to write, and most importantly, the calc to real, which is calculating from the pseudo axis to the real motors, and the opposite. But it's quite straightforward, and so people are doing it themselves. And as I said, pseudo counters, so it's the same as motors, except that the counters, they are not moving. It's an experimental parameter which can be measured during a scan. Sorry. And it takes multiple input and outputs, and they can be created in code or directly from this configuration. So this is the example here. For example, if you have a 4-quadrant diode, and then you want to calculate intensity and the center of the beam, for example. So you can give expressions directly in the BLISS configuration YAML file. And of course, you can do the same by coding. So regulation, I will not talk about it because I think there is this poster by Perceval tomorrow. So it's best to go and see the poster, but basically we can have a PID loop. The last thing I wanted to talk about is the BLISS data. So there is a poster also about that. But we have a group of users from ID10, users on ID10 from University of Tübingen in Germany. They wrote their own graphical front end, and using BLISS data API, they start BLISS scans, and then they receive the data from the Edgar detector directly through Lima or through the file, because we have this mechanism that if the data is not available in the detector anymore, it's the file. And then they can submit the jobs to our cluster, and then they have their feedback. So those applications have been written by users themselves. So as a conclusion, in fact, if you want to know more, we have BLISS satellite meeting on Thursday morning. So if you want to try BLISS, if you're welcome. More than half of ESRF beamlines, they run BLISS, and all beamlines will be converted in 2024. So it has been designed to fulfill the scientists' needs and the challenges as I presented before. And well, also, needless to say, but I say it, I would be happy if it's possible to start collaboration with people around BLISS or subjects of control. I mean, it's always very fruitful. And I'm done. So if you have questions, I don't know if we have time, sorry, because I speak a lot.